Have you ever wondered why we build rockets the way we do? For starters, they're huge, and despite that, they only carry very few people. In order to answer this question, we're going to become rocket scientists. By doing so, we will have a firm grasp of rocketry. Let's first consider a familiar example of how rockets move. In this video clip, the professor propels himself forward by releasing some mass at a constant speed, and as Newton would say, for every action there's equal and opposite reaction. This means a rocket is a machine that pushes some mass out in order to speed up in the opposite direction.
With that in mind, we're now one step closer to our answer. The next step would be to analyze the situation we've just described. In order to do that, we need to understand an important conservation law, and that would be conservation of momentum, which states in an isolated system, momentum is conserved. Now, when rockets and internal gases are moving one unit, the overall momentum is equal to mass times velocity. As stated earlier, the overall momentum of the rocket and fuel has to remain constant so long as we are operating under an isolated system. Therefore, if a small amount of gas, let's call it dm, is expelled at a velocity ve relative to the rocket, the overall momentum of the system is as follows. In order for momentum to be conserved, P1 needs to be equated to P2, and doing so will result into the following expression. Foiling out the expression will cause a lot of variables to cancel out, which ultimately will lead you to this expression. Before moving on, we're going to need to use a little bit of calculus. In particular, we're going to use two very important concepts. The first is a derivative, and second is an integral. Think of a derivative as a rate of something changing. In the context of our problem, dv represents a rate of change of the velocity. And just like with arithmetic, addition is the opposite of subtraction. A derivative is the opposite of an integral. Integrating both sides will result in this equation.
And there you have the Tsiolkovsky Rocket Equation. The beauty in this equation lies not only in its stunning simplicity, but also in its applicability to any body that accelerates by expelling some mass at a specific velocity. This equation was formalized by a Russian schoolteacher, Konstantin Tsiolkovsky.
By rearranging this equation, we can finally get to our answer. Let's say our rocket starts at rest to reach 11.2 kilometers per second with a constant exhaust velocity of 4 kilometers per second. Plugging these values in will result into 0.94, which means 94% of the mass at launch needs to be fuel. A plot of the rocket equation highlights one of the biggest problems we face with rocketry. You see, the amount of fuel to accelerate a rocket increases exponentially. Think of it this way. We have a rocket that has a payload at the top. That payload needs to be carried by a propellant, and that propellant also needs to be carried by yet another propellant, and so on and so forth.
That is why we use the rocket equation to determine what percentages of useful mass and propellant we can bring to our space adventures. Now, despite all that we're able to accomplish with the rocket equation, there's much more that needs to be done.